In the last section, we talked about how we can distinguish between the memories for a real event and memories for things we've imagined. But on the other hand, it is sometimes possible to create false memories, or false recalls that are believed by the brain to be accurate, but only if they're very similar to some real memories. For example, in some experiments, subjects were shown pictures of road scenes that included a yield sign. And later they were asked, "Did you see the stop sign in the picture?" A significant proportion then remembered a stop sign and continued to do so in future recalls. So the information activated semantically at the time of the first recall became part of the memory. It's even possible to create false memories of complete events, as in the experiments in which the memory of being lost as a small child in a shopping centre was created in the brains of adults known by prior discussions with their families never to have experienced such an event. In this case, being in a shopping centre was a common memory, and also being lost as a child. So it was possible to use simultaneous semantic recall of unrelated events to link information into a false memory, although that kind of memory could only be created in a small proportion of subjects, and recalls were not particularly vivid. How can we understand what's going on with these false memories? In the case of that picture with the yield sign, when we recall the picture, we don't get a perfect image. We are getting whatever columns can be activated on the basis of past expansion. Let's suppose that the visual columns within which the recall will be activated are in the array indicated by the purple arrow, and these are the parahippocampal columns that contain the information supporting the indirect activations. Once the memory has been recalled, the pattern of activation could look like this. The visual columns will probably have some recommendation strengths in favour of saying there was a yield sign, since there was a yield sign in the original scene. But on the other hand, any one column will have been activated in a wide range of circumstances which have some degree of similarity to the picture you looked at. So because the brain has probably observed lots of scenes in the past with stop signs and lots of scenes with yield signs, and some of these scenes had elements of similarity, these activated columns will probably have some recommendation strengths in favour of stop sign behaviour, although generally it'll be a bit weaker. But now let's suppose that "Did you see the stop sign?" is heard. Columns like the blue columns will be indirectly activated on the basis of frequent past simultaneous activity. Now remember that one parahippocampal column isn't unique to one experience. It's a particular combination of parahippocampal columns that enables the brain to retrieve an experience. So there's a chance that, because of other experiences, some of the active parahippocampal column receptive fields also happen to include those blue columns. If the blue columns are already part of some of the active parahippocampal fields, then because the synaptic weights in each direction are increased by simultaneous activity, they will tend to be activated again if the same parahippocampal columns are activated in the future. So extra recommendation strengths in favour of identifying a stop sign will have been introduced, which could lead to those recommendation strengths being stronger than yield sign strengths in future recalls. So let's have a look at this at a bit more detailed level. On the left, there's a bunch of neurons from the deep layers 5 and 6, coming from a range of columns in the parietal cortex. On the right, there's a bunch of P3 population neurons from a range of columns in the parahippocampal cortex, and the dendritic trees are all simplified down to one branch for illustration purposes. Deep neurons in the parietal cortex make synapses onto the P3 parahippocampal neurons, and the P3 neurons project back to the deep neurons. And if one P3 neuron gets inputs from a group of parietal cortex deep neurons, it projects back to those same deep neurons. And of course, this is the connectivity that supports episodic memory retrievals. Suppose the neurons in the red squares were active during an episode of receptive field expansion that occurred when looking at a picture that included the yield sign. The active deep neurons and the active P3 neurons are colored red. Some of these deep neurons will have recommendation strengths in favor of saying there's a yield sign, but because there can be similarities between the scenes containing yield signs and the scenes containing stop signs, some of the neurons could also have recommendation strengths in favor of saying there's a stop sign. In general, the total yield sign recommendation strength will be greater than the stop sign recommendation strength. The synapses receiving inputs are colored red, and some neurons outside the groups have active synapses. But because of the episode of receptive field expansion, when looking at the picture, the number of active synapses on a deep neuron in the group will be larger than on a neuron outside the group. Similarly, P3 neurons in the group will have more active inputs than P3 neurons outside the group. And as a result, if a subset of the deep neurons is activated and their outputs released to the parahippocampal cortex, there'll be a tendency for activity to converge on this combination of active neurons. Now, think about the neurons active during an episode of receptive field expansion that included a stop sign. But otherwise, the scenes had quite a lot of similarities. Perhaps both include a junction between two paved streets, cars, houses lining the streets, trees and bushes in the gardens, and so on. The neurons in the green squares could be the active sets during the scene with the stop sign. And the sets partially overlap with the sets active during the scene with the yield sign because of the similarity. I'll indicate the active synapses during the stop sign scene in green, and once again the number of active synapses onto deep cortical neurons in the set is greater than outside the set, and similarly for the P3 neurons inside and outside the set. Now imagine the situation when an attempt is made to recall the scene with the yield sign. Initial activation of a somewhat different group of parietal cortex neurons by words correlating with the scene, followed by convergence on this active configuration. But suppose, in addition to the words invoking the scene, the question was asked, did you see the stop sign? And in response to those words, additional neurons in the parietal cortex, colored pink, were activated. And of course, these neurons will have some recommendation strengths in favor of saying stop sign. These extra parietal neurons contribute some additional active synapses to the P3 neurons. And as a result, a couple of extra P3 neurons have enough input to fire. Their firing provides inputs to some additional synapses in the parietal cortex. And because of the reciprocal connectivity, these inputs are enough to maintain the firing of those two additional parietal neurons. This means there's excessive numbers of active neurons in both areas, and in this situation, inhibitive connectivity will tend to reduce the numbers. Now, that parietal neuron on the left has fewer active inputs than this parietal neuron outside the red set, although this extra firing neuron doesn't have as many active synapses as the other extra. So the inhibition will tend to leave this extra neuron firing and inactivate the other two. That will extinguish their active synapses in P3. So, in P3, the two active neurons outside the set have as many active synapses as a couple of neurons in the set. So perhaps inhibition may inactivate a couple of neurons, one inside and one outside the set, and extinguish the activity on the synapses in the parietal cortex. So at this point, we've got a different equilibrium configuration of reciprocal activity between the two sets of neurons, like that. But recall that when there's a reciprocal activation between the deep parietal neurons and the P3 parahippocampal neurons, synaptic weights increase. As a result, this new configuration could tend to become the stable point for future recall processes. The loss of the neuron in the old set and addition of a neuron from outside the set may be sufficient to shift from a predominant weight in favor of yield sign to a predominant weight in favor of stop sign. So a false memory of the stop signs being established. Now, note that this has been a very simplified example. In reality, individual synaptic weights vary, and dendritic trees are heavily branched with separate integration of synaptic activity on each branch. These factors will make it harder to confuse information in the way we've just described. So it's possible to introduce false information into a memory, but only in fairly special circumstances, and even then it may not always happen. The information coded in P3 neurons generally enables good discriminations between different events, so major memory errors are relatively uncommon.